Let's go ahead and take a look at some more problem-solving strategies. The three remaining that we'll focus on in this class. The first one, the first three we went through. Here's the fourth strategy, looking for patterns, which again, I think we do all the time, but it works best again when you have lists of data, number sequences, visual patterns. Um, when you see something that just stands out as, I think I see a pattern, right? And it's important to remind you our brains are pattern making machines. They want to make predictions, they want to connect ideas, right, together. So our brains are wired to do that. So just keep that in mind. Um, we would start off in class probably with this little warm up question of like finding these missing numbers. So again, as you look at it, I know I have the answers already put into there, but you would want to challenge yourself there, or even again have someone that's close to you, see what they would think about. Just listen to their thinking as they try to put in these numbers for the patterns. So looking for patterns, we have an example here. This is a famous triangle, which again we'll learn later in different applications. Look it up if you want for now. And I think I have it linked in our textbook. You have a link to Pascal's triangle. Let's see if I did put it in there. Yeah, the Pascal's triangle, there's a link to it. It explains all the famous um, things that are related to Pascal's triangle and how it appears in our world. But let me get back to the actual problem. Just finding the next rows in this process. Turns out that they're related by just adding them together. 1 plus 4 is 5, 4 plus 6 is 10, and so forth. So just that simple addition to complete this creates Pascal's triangle, which then is connected. Like I said, if you link and just browse around, the many awesome uses and findings in the world of where Pascal's triangle just shows up somewhere. So keep that in mind. We'll get to this strategy a lot during the course too, looking for patterns. Another, again, classic for me personally is I like to make lists. Whenever I'm kind of confused, I just make a list or make a table, try to organize everything. What are all my possible outcomes? This is good when you have limited solutions because you can put everything together, working on probability problems and so forth. So keep that in mind when we have this list here, how we would solve a problem. And I start here to draw things. I make guesses. I make lists, and I still do this to many aspects of my life. So keep this strategy in mind. Just start writing stuff down, organizing them in some way. So a classic problem is this kind of simplified, we have multiple choices. In this case, real simplified problem, 3 types of sandwiches, 2 kinds of sides, and 2 different drinks. How do we do it? Well, let's make a list of all the possibilities. Turns out there's 12 possible answers, right? When you group them together. And then, like I said, the textbook has a nice set of tables of how to organize it. Sandwich 1 with drink 1, side 1, drink 1, sandwich 1, side 1, drink 2. And then you just continue in what we call a systematic way, in some organized fashion. And then you got your answer. You could see this works well when we have a limited number of options. At some point, we would see a pattern, and then we could just make a prediction, which we're going to do and solve a simpler problem. You start small and you let it grow. So to solve a simpler problem, as we look here, a band wants to decide the order of 5 songs in their concert. How many ways, right, can they arrange them? So a set list, if you go to concerts, you want to know what the set list is. In this case, it's how many different ways. What are they going to end with? What are they going to begin with? Right? These are questions. If you go to a concert, you ask. Are they going to play my favorite song? Well, that's another question that mathematically we could probably answer to probabilities by looking at the set list. You've probably played that game where if you're going to a concert, you look at the set list and you see what songs are being played, right? That would be a probability question and looking for patterns to make predictions. But in this case, let's say there's 5 songs. How many different ways? And again, this is a simplified version of a more complex problem. How many different ways can they play those 5 songs in what order? Turns out to be 120 ways over here. you will see over here. And that comes from just a pattern, but starting with a simpler problem. What do I mean by that? Imagine that you only had one song, one way. Two songs, there'd be two ways. If they had three songs, there would be three ways. Four songs, 24 ways. Now, the three songs makes a little bit sense. You could see I have a list here. 1, 2, 3, 1, 3, 2, right? You get 6 different ways. The 24 comes from seeing a pattern, right? Starting from a simpler one. And so the pattern I see, it's 1 times 2, and then 2 times 3 is 6. The number of ways, sorry, 1 way times 2 is 2. 3 songs times 2 ways is 6 ways. And then we're going to do, in this case, to get the next one, right? 6 ways times 4 songs is 24 ways to play it. And then we're going to end up with 24 times 5 is 120. So that pattern emerges when we start with trying to solve a simpler. This is not a trivial one. I don't expect you to master it. It would take a little bit longer for us if we're going to do it out by hand. It might take you maybe 5 minutes. I just try to explain it quickly. And then in class, think about, we would have students think about, how would you solve these? Don't solve them, but how would you solve them? What strategies work best? And then we would spend a little bit of time trying things just to see what you would do when we think about solving a simpler problem, looking for patterns, making organized systematic lists and tables. What would you do with each of those? So where are we? Right there. You think about that. And before we leave chapter 1.5, we have this very ending, just some terms and some ideas I want you to think about. We have what's called a number sequence. So we'll talk about this ideas. It's just a list of numbers. You may already know this. I just want to define this. And then the 3 dots, the ellipsis, which means go on forever, means the pattern continues forever in the same way. 1, 2, 3, 4, dot, dot, dot. So again, just to bring together some of the ideas that we'll have in the class and some of the language we're going to be using. This idea of sequences and ellipses going on forever is connected to an important way of thinking in this class, which is through inductive reasoning, right? A way of making predictions based on patterns. We don't know for sure. This is the key thing about inductive reasoning. We're not 100%. There's not proof that that's the next thing that's going to happen, but it's our best thinking based off of patterns. Inductive reasoning is based off of patterns. When you make a prediction, you're using inductive reasoning, which is different than what we call deductive reasoning, which many people are used to in mathematics, right? About deductive is about using facts that we know for sure. Inductive reasoning is about noticing a repeated pattern and making a prediction, which again is in contrast to deductive reasoning, or it's a way of thinking that starts with general principles and applies them, right? You have specific facts, and this fact leads to another fact. There's a lot of algebra stuff where you solve and make proofs, right? It's used to construct logical arguments, prove theorems, validate something that is true. In elementary school, though, we primarily use inductive reasoning to explore patterns. And then we use deductive reasoning as we advance to more forms of mathematical thinking as we get closer to algebra, because we'll use proofs in algebra to show something is true, right? But both reasoning do work together.